Okay, let's go ahead and take a look at this problem. So let's write down the parameters. So down here, I'm going to write down the FOV in the x direction equals the FOV in the y direction. And that equals 10 centimeters, right? Okay. So what parameter do we derive from the FOV? Delta K, right? So in this case, delta Kx and delta Ky are the same. And so that's just 1 over 10 inverse centimeters. Okay? So that's the first thing you'd write down from what you're given. Then the next thing we have to figure out is the delta K is going to be equal to gamma over 2 pi. And what we notice is also here, in every time step we take, we're just either moving a delta Ky or a delta Kx, right? So we just have to figure out one delta K, right? It's just how much do we want to move that much each time step, okay? So each time step we have to move this delta K. So delta K is just equal to gamma 2 pi times the amplitude of the gradient times delta t, right? We're given delta t as 10 times 10 to the minus 6 seconds, right? So then we can just solve for g equals, or let's see, this was 0.1. You're given gamma over 2 pi is 4,000, so it's going to make the math easy. Okay? And then taking the delta t to the other side, that's, what is that going to be? 10 to the 5th, is that right? Okay? This is going to be equal to 10 to the 4th over 4,000, right? Which I think equals 2.5 Gauss per centimeter. All right, so that's the only math you have to do for this problem. Everything else is just looking at it and drawing it out, which we'll draw out now. All right, so let's go ahead and draw our pulse sequence. So we're going to have gx as a function of time, and also gy as a function of time. All right, and then we're going to just draw the time steps: 10, 20, 30, 40, 50, so on, okay? And then down here as well, 20, 30, 40, 50. And the nice thing we know is the gradient's always going to be either 2.5 or minus 2.5. That's the only thing we have to draw because we're always taking these steps, okay? So let's look at from 0 to 10. Is the gx gradient on at all? No, so it's just 0 here, right? What's the gy gradient going to be? Yeah, it's minus 2.5. So it's going to be like this, right? Okay. Then what happens between 10 and 20? Is the gy gradient on at all? No, we turn it off because we're not moving in ky anymore. And the gx gradient is going to be what? It's going to be plus 2.5, right? Because we want to move in the positive x direction. Okay? And then what happens between 20 and 40? What gradient do we have to turn on there? Yeah, so we have to turn the gy gradient on positive, right? Because we got to move up. And what about the x gradient? It's 0, right? So it's just off. Okay? And then you can just go on and on and on, right? So it looks sort of intimidating, but once you do it, it's actually fairly straightforward. Go ahead, question.
So what would tau be in this scenario? Is that just delta t?
Yeah, so that's the thing about spin warp has certain terminologies because it's used so often. But in general, you can think of a gradient as just a function of time. And so the delta t in a gradient, in an MRI system, there's the rate at which you can play out the gradients. So the fastest, for example, on our system, we can update the gradients every 4 microseconds. So that would be the limit on delta t. And so in general, you define the gradients as a function of time. But when you have something very stereotypical like spin warp, where there's a width, then you might give it a special name like tau or tau sub x, something like that. So spin warp has got sort of specific terminology, but other sequences are more generic. It's just a function of time. Other question?
Where would resolution play in this?
That's a great question. So what is the resolution that we're achieving here? Any ideas? Go ahead. 2.5 centimeters. Right, okay. So the resolution is 2.5 centimeters. So let's see if this pole sequence meets that resolution. Okay. So let's see. I didn't leave any space for that. So we know that WKX. So in this case, the resolution is the same. So it's just W of K, either X or Y, doesn't matter, is equal 1 over the resolution, right? Which is 1 over 2.5. Okay? So that means this width had better be 1 over 2.5. Okay? And the question is that? So what did we say each of these guys is? 0.1, is that right? And 1 over 2.5 is what? 0.4? Okay. So is this width 0.4? Yeah, it is, right? So we have gone out far enough in K-space. Okay. So does that answer your question? Great. Any other questions? Yes?
In the real world, would this actually be a full string, or would that be just a series of sine waves that would do the actual, like the polar helical?
Yeah, that's a great question. So the question is, would we actually use this? So this is what's called a square spiral. If you were doing your PhD at Stanford in the late 1980s, this would have been part of your thesis, and this was actually submitted as an abstract, I think, to one of the scientific meetings. Now, 30 plus years later, you know, it's just an example. So no one really uses square spirals, but Archimedean spirals are used a lot. So an Archimedean spiral would look like this. So those we use all the time because it's a super fast way to go through K-space, but it's just hard to do it as an easy example. So we do the square spiral for the easy example, but in general, you generate these spirals, and there's lots of variations of spirals.
Would that just be all sinusoidal waves?
Yeah, so the waveform of that, so if you think about what it would look like, it would be like this. So you'll have to have gradients that look like that. And there's lots of variations of that. Okay? Any other questions? Okay. So, and on that note, you know, we've just shown you a couple examples of ways to go through K-space. Almost anything you can think of has been done, or, you know, lots of variations have been done. So let me see. I have some. I'm going to just do it on this page, okay? So it's a blank page. So for example, there are things called rosette trajectories that go like this. So that might be a rosette trajectories. There's even people who have just played around with random sampling of K-space to see what happens if you do random sampling. If we get to have some time for compressed sensing, we might talk about random sampling. There's also, you know, we've talked about 2D, but there's also 3D trajectories if you want to do a 3D encoding. And so people have come up with like cone trajectories. So just any way you can go through space, people will try it. And each way may or may not have some advantages and disadvantages. But it's the MRI machine is very flexible. It will basically, within the limits of the hardware, you can do whatever you want. Okay? Any other questions? Okay. So I'm just going to spend the next few minutes talking about some, these are sort of optional topics, but it's sort of one of these things where if you do MR, you're like, well, why is that done that way? So this is more, especially for those of you who are going to do more MR, these might answer some questions for you as you're going through your career. So typically when we're looking at the matrix size, you know, there'll be things like 256 by 256, or maybe, you know, 128 by 192. And it's typically always an even number, okay? Now, in the really old days, you know, 40, 50 years ago, it was really advantageous to stick to powers of 2, okay? Because at that point, FFTs, fast Fourier transforms, were really just fine-tuned for powers of 2, okay? And so therefore, it was a really huge advantage to always stay with a power of 2, like 128, 256, 512. Nowadays, there's much better algorithms that can take, you know, non-powers of 2 and do them very quickly. But still, we typically do an even number. And then the question is, with an even number, how do you actually cover K-space? So for example, let's say we had 4 lines, okay? And a typical coverage of K-space will require 1 line, 1, 2, 3, and 4, okay? And the question is, well, what happens to this line here? why don't we need to acquire that line? It seems like we're missing some data. Okay. So one answer is, in certain cases, like we talked about in a previous lecture, if things are ideal, you can sort of get away with just partial Fourier. You don't need all the data because there is some symmetry in Fourier space. But also, even if you wanted all of Fourier space, it turns out that this line, given the resolution, is sort of redundant. Okay, the information in this line is actually already captured in this line. Okay, and so that's the explanation. Sort of intuitive feeling of that is it's really due to, once I've picked some sampling, like say, for example, delta x here, and this is ky equals 0.5, and this is ky equals minus 0.5, so it's on the other side. If you notice, with this delta x and this delta y, okay, especially the delta y here, if you look at these, with that resolution, everything is going by 180 or minus 180. So we can't tell whether it's a positive or negative frequency. So just at that outer line, there's that ambiguity. So you don't need to acquire both lines. All right? So that's assuming that this was your resolution that you wanted. Obviously, if you looked at things in between these voxels, then the phasors would be pointing in different directions. But once you say, I'm OK with this resolution, then you don't need to acquire any more information. So that's sort of one thing that you might encounter that in MR. The other thing that is you'll encounter is, we've talked a lot about windowing. So we talked about this concept that if I have my Fourier data here, right, but I don't want to acquire all of it because I want to save some time, I might just acquire data in some window. All right, and this is our rect function here. Okay. But the problem with a rect function is when we multiply by a rect function, we're convolving with a sinc function, which has lots of little ripples in it, right? And so this is an example here. If I have a sharp edge here, and I convolve it with a sinc function here, I end up with this blue curve here, and you can sort of see it has quite a few ripples in it. Okay? And so, for example, this image you see here, all these ripples here, that's due to that sinc function. All right? And this is something where if you have a hard edge in your body, like let's say between bone and tissue, you don't want to sort of see ripples that are an artifact where you might think it's something else. Okay? So one solution to that is you can just make this window bigger. Okay? So if I make this, let's pick a different color here. I could make the window bigger, right? Spend some more time. That would make this sinc function smaller, right? So then these ripples would be finer. It would happen more quickly and die more quickly. So that's one solution you could do. The other solution is, which is also somewhat related to what we did in CT with the Ram-Lack filter, is instead of using a rect function, you would use something like a Hanning window, a smoother function. So you smoothly chop off case space. So instead of convolving with a sinc function, which has all these ripples, you're now going to convolve with something that's smoother. Okay? And so what that means is there's a trade-off. You notice here, this one leads to this black line here. So it doesn't have the ripples, but it's transitioning slower, whereas the sinc function does a very fast transition but has these ripples. So there's always that trade-off. If you really want to get rid of the ripples, then typically you'll apply some apodization. All right? So this apodization is a concept that goes across modalities. It's in MR, it's in CT, it's also when you do ultrasound next quarter, if you take U280B, it's also in ultrasound. This idea that whenever you have these rect functions, they have these ripples, which are not always desirable. And so the trade-off that we usually make is we have a smoothly varying function. Question? Is there a Butterworth filter? You know, you can have any shape you want. A Butterworth filter is what's known as an IRR filter. So it has an infinite impulse response length. So to implement, when you're acquiring finite data, you probably want something that's just more defined within a certain a fixed interval. Yeah. Okay.
These names also correspond to certain filters in signal.
Yes, these are all filters. There's Hanning, Hamming, Blackman-Harris, yeah. So there's basically lots of windows, and they are basically filters, right? Because you're convolving with these functions. Okay. Anything else? Okay. The last thing I want to talk about is aliasing and bandwidth. So far we've told you that if you have a really big object, so we've told you that delta k. Oops, let's see what happened there. Okay. Delta k equals 1 over the field of view. Okay. So the question comes out, what happens if the field of view is really, really long? Right? Like in this case, let's say you want to image someone's spine, and that's a really long FOV, right? Maybe it's over 1 meter or so. Then the problem is that as the FOV goes up, the delta k goes down. So you're going to have to sample much more finely in k-space, and that's going to take more time. And you're like, well, I don't really want to spend that much time. You know, someone's got back pain. They can't lie there for 30 minutes. I've got to scan them much more quickly. So one question is, how do you deal with really large FOVs? And especially with the spine, the issue is if you're scanning and this is your direction you want to scan in. There's actually, you only care about this part of the object, right? The spine, and you don't care about the head, okay? But if you don't, if you set the FOV to just characterize the spine, if that's your FOV, then the head is going to alias into your spine, okay? And that's not going to be good. So you have like a picture of someone's spine and their head's like right in the middle of it, all right? So the question is, what do you do? And it turns out that there's a really nice solution in MR, which is the fact that when we apply the gradient, so this is the readout direction here. So we're imagining that there's this gradient here. Okay, so it's going from slower here to faster here. Okay, so the spins here are faster than the spins here. Okay, and so there's some frequency. So this might have some frequency FH, and this has some frequency F sub L. Okay. So in this example, let's say we just want, instead of the spine, we just wanted the head. We wanted the FOV to just acquire the head, okay? And we didn't want the spine to be in the image. So this is typically what happens when we're imaging someone's head. We want just their head. We want the readout direction this way, and we don't want their spine in their head, okay? So the idea is, if I look at a spin here, right, it's going to be processing really slowly, right? Because its frequency, it's going to be down here, okay? So it's outside of this bandwidth here, okay? So depending on where things are in the readout direction, that determines the frequency of the spins. And so if I can just apply a filter that just keeps the spins in this region, then I can basically filter out all the information coming from these spins, all right? And that allows me to get around it. So I can set my FOV to just cover this region. I don't have to have the FOV cover this entire region. All right. So the way that's done is, we saw this before. This is the MR signal. This is the demodulation here. We apply this low-pass filter. Okay, that filter just says any spins that are processing at frequencies I don't care about, just get rid of them. All right. So what that means is, for example, if this was the FOV of my object, so that's like the whole body, I apply a filter that just says, just give me the spins in the area that I care about, then the resulting image will just be that area that you care about, okay? So what this means is, in practice, this is from the GE Medical Systems Handbook, is you typically want to always put, in this case, F stands for frequency, and that's just another name for the readout direction. You always put the frequency encoder readout direction in the long direction, and that allows you to get around having to make the FOV really big. All right, so that's something that you'll actually see used in practice pretty much every day. Okay, so people who are doing every day, there's probably at UCSD many scans of heads, and they're typically done with the readout direction this way, for that reason, so they don't alias the spine. All right, any questions on that? Okay, great. So we are going to now change gears a little bit. So we've talked about how to go through K-space, and we're now going to switch gears and talk about relaxation and contrast. Okay. So what we have here are 3 different images of the same head. Okay, but they look really different. All right. So this was just someone lying in the scanner for maybe half an hour, and between the different scans, so what we have here is what's called T1 weighted density weighted, and T2 weighted. By just changing the amplitudes and the timing of all the pulses, we actually change what information we can get out of the MR scanner. So we want to spend the rest of this lecture talking about how we actually do that. All right? So just to review, although we haven't gone through the specifics, the basic idea of an RF, of the MR experiments is we start off with what's called an RF excitation, where we put some energy into the system that takes the magnetization from being longitudinal, and in this case we've applied what's called a 90-degree pulse. Okay? So we've just flipped it into the transverse plane, and now it's going to process around. Okay? So if there was no relaxation, so this is no relaxation. Actually, sorry, that's the RF pulse that's being applied. Okay, so if there's no relaxation, the MR signal could just go on forever, right? But nothing lasts forever, so things are going to return to equilibrium. And the equilibrium is, in this case, there's zero magnetization in the transverse plane. Okay, so this is what's known as the free induction decay. Also abbreviated FID. Okay? So that's the signal you get. If you do the MR experiment, you tip the spins, and then they spin around, process for a little bit, and then after some time, it's gone. All right? So that sets a limit. You have to acquire your data in this time window, because if you don't, you have nothing to look at. So here we have another picture of the free induction decay. So this is what the signal looks like if you look at it on an oscilloscope. This is sort of what the magnetization looks like. You've tipped the magnetization down here to the transverse plane, this XY plane, and then it's just going to process and then disappear. All right? So there's really two types of relaxation. The two main types of relaxation we need to talk about. There is relaxation of the longitudinal component, the M sub Z, and there's relaxation of the transverse, the MXY component. Okay? For longitudinal, it's what we talk about is a T1 time constant, or T1 recovery. Okay? And that's the return to equilibrium of the M sub Z component. For the transverse, we talk about T2, which is the transverse relaxation, and that's the return to equilibrium of MXY. Okay? So the equilibrium of this is going to be 0, and the equilibrium of this is whatever the equilibrium magnetization is. Right? So just basically we want to look at the return to equilibrium, and if we play our cards right and design this pulse sequence correctly, we can take advantage of that return to equilibrium. So let's look at the first part, which is longitudinal relaxation. Okay? So I'm just going to give you the equation of motion, which is just this. The longitudinal relaxation follows a first order differential equation with a time constant of T1. Okay? And it's always trying to get back to this M sub 0 term. Okay? So if there's any difference between MZ and M0, it's going to dm dt is going to be non-zero. It's going to try to drive it back to M sub 0. So the picture is fairly simple. It's always trying to get back to this equilibrium magnetization, and it follows an exponential recovery. Okay? So for example, let's say we start off at 0 here. Then the equation of motion is just simply M sub 0, 1 minus e to the minus t over t1. Okay? So those of you, for example, who have done, probably everyone here has done basic RC circuits. This is sort of like, the RC circuit time constant. Okay? So this is what's due to, a process that's called stimulated emission due to dipolar interactions. And the idea is that, we've excited these spins, and so certain spins have a higher energy, okay? So we put some energy into the system. And then if we just wait around for spontaneous return to equilibrium, we'd have to wait around a long time. So it turns out that it requires what's called stimulated emission. These spins are hanging out, and in order for them to give up energy to the environment, we need to give them a little kick. Okay, that's called stimulated emission, and the kick has to be at the Larmor frequency. Okay, so it's a certain frequency of kick. Once they get that kick, then they go, okay, I'll give up my energy to the lattice. Okay, and that's going to determine how T1 varies with different tissues. So let's look at sort of that variation. So what we have here is this is magnetic field strength. This is from the Nishimura book, so it's varying from about 0.2 Tesla to 2 Tesla. Okay. And you can sort of see that here, gray matter is in the brain, white matter, muscle. These tend to have fairly higher T1s. So things that are more, so things in the brain and muscle have higher T1s. And then the noticeable thing here is that the fat has a very short T1. So we want to sort of at least understand, for example, why does fat have such a short T1? But it's this fact that different tissues have different T1s that allows us to create the contrast. Okay, and we'll see how to do that. So here's one picture. So the idea is that every proton has its own magnetic field. So this is, for example, showing a proton here, and it's the magnetic field around the proton. Okay. So let's say that this spin here, the spins in this guy have been sort of are just hanging around, and they haven't emitted their energy yet. Okay. And what it needs is a kick from the environment, a little kick to tell it give up some energy, to have some stimulated emission. All right. So how does it get that stimulated emission? Well, imagine that things are always rotating around. So imagine that in this guy, this proton here is rotating around this stationary proton. So it's just sort of spinning around it. Okay. So the molecules are sort of the configurations are changing, and so this proton here is going to experience different magnetic fields. Okay. And if it rotates at the rate that the magnetic field frequency it experiences is at the Larmor frequency, then stimulated emission can occur. All right, and that's shown here, where when the tumbling rate here is just right, then we can have a very short T1. So this is the T1. So this is where we're getting lots of stimulated emission. Okay, because things that like let's say we're at 3 Tesla, so 127 megahertz. So if the molecules are tumbling around 127 million times per second, then that's giving it the right kick to let it release its energy. Okay, so if you're in something like water, things tumble really, really fast. And so what happens is that the tumbling frequency is not at the right rate for you to do the stimulated emission. So then you have very long T1s. Okay. And if you're in something, a tissue where there's like ice, where there's no tumbling, or the things are very fixed, then also your frequencies are too low. So you're not going to have the stimulated emission. So this is from a website that's really good. I mean, it's called MRI Questions. Basically, any question you have about MRI, this guy has an answer for. So I highly recommend this, especially if you're doing any of the MRI projects and you don't understand something. This is a really great site. He's a retired professor of radiology who just spends all his time now just updating this website. I think it seems like it. So it's a really good website, and he terms this like the Goldilocks principle. You know, like this is too hot, too cold, just right. Okay, so when the tumbling rate is just right, you get the stimulated emission, and that's when the T1 is going to be the shortest. All right, because then it's easy for you're encouraging the spin to give up its energy. So in this case, free water is tumbling too fast. These macromolecules here are tumbling too slow, but things that are sort of bound water, okay, typically have the right tumbling frequency for the frequencies we're talking about. So let's take a look at what happens with, for example, field strength of T1. So in fact, if you look back at this curve here, you see that the T1s are increasing with field strength. Okay, so as I make the magnetic field stronger and stronger, that T1 goes up. Okay, and so what's happening as I make the magnetic field strength get stronger? What's happening to the Larmor frequency? It's also increasing, right? Because remember, omega equals gamma B. Okay, so if I increase the B, I increase the frequency. Okay, so then if we go back to this curve here, what happens is, so this is the field strength of T1. And so if I go from this frequency to this frequency, okay, then it turns out that the proportion of spins tumbling, so that's just so these are the macromolecules that have the right tumbling frequency. The number of them that tumble at those higher frequencies is just less, okay? And whereas at the lower frequency, there's generally more that are tumbling at the right frequency. And so just for the range of things that the biological ranges tissues we're looking at and the field strength we typically use in the clinical environment, we do see this increase in T1. Right? And then this is just a example of fat where you have these sort of bound water, but yet you also have these CH2 groups that can rotate, and so it just turns out that fat just does tend to have these rotational frequencies that allow it to have a short T1. Okay? And we'll see some examples of how we take advantage of that for the images. Right? Any questions on T1? Okay. So the next thing we're going to talk about is transverse relaxation, or T2 relaxation. And it's got a very simple equation of motion. Basically, the derivative is just minus mxy over T2. And so you know this is going to just decay with a T constant of T2. Okay? The equilibrium, any time this is not zero, there's going to be some derivative that's non-zero. So this is going to drive this to zero. Okay? So that's the equilibrium. And it turns out that T2 is largely independent of the field strength. And it is really dependent, it's what's called spin-spin interaction. So I think I have a picture of that. Let's see. Well, let's go through what it looks like first, and then we'll go through the mechanism. So what it looks like is fairly simple. It's just, if I start off at some m0, then I just decay like this, m0 e to the minus t over t2. Okay? So it's the decay of the magnetization. So let's look at some T2 values. So what we have here are some values for gray matter, white matter. And then we have this one, CSF, which stands for cerebral spinal fluid, which is the fluid that bathes your brain. It's fairly close to water, so you notice it has a very, very long T2, like an order of magnitude greater than the tissue. Okay, so let's try to understand why the T2 of water is so long. Okay, so the issue comes about from what's called dipole-dipole interactions, and in this case, imagine you've got, say, this is dipole 1, dipole 2. These are two spins. Okay, and so let's say I have a spin here, and it's processing at the Larmor frequency. Okay. And then if I have a spin here, this also has a magnetic field associated with it, right? So this spin feels not only the main field, but it also experiences the field from this. So for example, if this makes this field stronger, it's going to process a little faster, okay? This spin here will maybe experience this field as well, but it maybe experiences a slightly smaller field from this guy, so it's going to process a little slower. So what's going to happen, this spin's effect on these two spins is going to have a differential effect. And so over time, they're going to get out of phase. Okay, so that's the phasing that causes the T2 relaxation. Okay, so if this spin is very stationary, then these spins sort of, over time, experience that difference in magnetic field, and so they're going to get out of phase very easily. But let's say this spin here is just moving all around like that. Okay, so on average, what field will this spin feel from something that's just randomly moving around? So sometimes it feels a positive, sometimes it feels a negative field. On average, what do you think it's going to average out to? Zero, right? Basically, if, for example, the field it feels is just varying all over the place, right, from this guy, then over time, it's going to average out to zero. Similarly, this guy is going to feel a zero field from this, if this is really tumbling around very quickly. So it turns out that if you have something like a liquid where things are tumbling around really quickly, then it's something called motional averaging, and so the spins don't really have an effect on each other. Okay? So what you see is when there's a very fast tumbling rate here, you have a very long T2. Okay? And when it's very slow, like for example in bone or tendon, where these spins are really sort of bound, then you get a very short T2. All right, so the tumbling rate really affects your T2 in that fashion. Okay, so we have this distinction between T2 where you sort of see as the tumbling rate gets faster, the T2 gets longer, whereas for T1, there's sort of this sweet spot, okay, where you have to be just right because you have to be tuned to the lower frequency. All right, so that's basically the sort of the hand-waving argument as to why these things occur. In terms of, if you think about the spins, what happens macroscopically is here I've tipped the magnetization in the transverse plane, and because of that, those fields, each spin is feeling slightly different fields from its neighbors. We end up with this dephasing here, where spins just get out of phase. Okay, so if I think about the vector sum of all these spins, if they get out of phase, what happens to the vector sum? It decreases, right? And so that dephasing is what causes this decrease in transverse magnetization. So over time, we're going to end up with this. All right, so that's what's happening. It's the dephasing of the spins. That's the T2. And so this is just sort of summarizing T1s and T2s. You can see water has both a high T1, high T2. Tendon, look at the T2 of tendon, super short, 5 milliseconds. Okay? And what this means that is in a lot of MR, we can't even see the tendons unless you use something called ultra-short echo time, which one of the projects is going to talk about for lung imaging. So there are new technologies where this is being used. All right. Okay, so are there any questions before we have you guys work on this problem? Okay, so let me explain this and we'll open up the poll. So Dr. Block has a vial of liquid with a T1 of 1,000 milliseconds and T2 of 1,000 milliseconds. Okay. He adds some gelatin to the vial, you know, like Jello gelatin or whatever, or agar. Shakes it up, allows it to gel, and then he measures T1 and T2 again. So the question is, of these choices, what would be reasonable values for the T1 and T2 of the new mixture? Okay. So I think this one is, let me see, bring up the poll. Yeah, so this one is just, you can click on whatever you think. So it's a multiple choice. So just go into the website and click. Okay, let's take a look at this. So right now the scoring is 4%, 11%, 46, and 39. Okay, so let's take a look at each of these answers and just work through them and see if we can sort of figure out what might be a reasonable answer, and there might be more than one reasonable answer. All right, so let's look at A. So one possibility is nothing changes, but how likely is that? Not very likely. Okay. Second one is T1 increases and T2 increases. Okay, so why would that be not necessarily a good? Why would we think that probably won't happen? Right. Yeah, so we'd expect at least T2 to decrease, right? We're not sure about T1, but T2 definitely has this, with tumbling rate. Okay. What about this one here? T1 is down to 100 milliseconds and T2 is 500 milliseconds. Why might we rule this one out? Go ahead. Right. T1 should be larger than T2. Okay, so we didn't really talk about that, but there was this, I think there was a note here. So it is just a fact that, and it can be shown that T1 is always larger than T2. And physically, that it's because the mechanisms that give rise to T1 can also give rise to T2, but it's sort of a superset, and so anything that causes T1 will also cause T2. Okay, so in general, just know that T1 is always greater than or equal than T2. Right? And so we could rule that. We can rule this out, and we can also rule this one out. Okay, so we're just left with these two answers here. So let's see, is there a reason to believe either one is more preferable than the other? One's less extreme. So which one is less extreme? E? Okay, less extreme. Okay. So yeah, so basically the T2s are both reasonable, right? We've really decreased the T2, and so that's possible. The gel really makes the tumbling rate much lower. And then in terms of T1, we actually really don't know where we are, right? Because remember, the T1 curve goes like this with a tumbling rate, right? So if we were here and we added the gel, then we would expect to move in this direction, right? In which T1 would go up, and so we'd pick E. But let's say we were here and we went here, then we could expect T1 to go down. So actually either one, we don't really know the shape of the curve, so either one would actually be a reasonable answer. Okay, any questions on that? Okay. So we're going to just briefly go over what the Bloch equation says, and so essentially the equation of motion for the magnetization, previously we talked about precession. Now we just add on terms for transverse relaxation and longitudinal relaxation. Okay. We're not really going to go through the derivation, but just to remind you that if we didn't have relaxation, then we just simply have this very simple solution here, that in plane, the magnetization just precesses around. All right. Now we add in these magnetization terms along the diagonal, and we also have to add this term. And so that's what the matrix equation looks like. And it turns out we can break it into a z component. So this is the z component. This is the solution here, which I think you're asked to derive that on the homework. So at least you know what the answer is. Okay. And so if the initial condition is 0, then it's simply starting at 0 and recovering to m sub 0. And we can also, it turns out we have a lot of flexibility in MR. We can actually take that magnetization, and we don't have to stop at 90. We can go all the way to 180. And so in this case, it's called inversion recovery. And so we start off at -1 and we go to m sub 0. So this is minus m0 plus 0. Okay? So those are the two of the most popular solutions in terms of whether you're starting at 0 or they're starting at -1. Those tend to be the most commonly used. All right? But in either case, the intuition is simply things are returning to m sub 0 with T1 time constant. That's all you really, sort of the picture you have to have in your mind. The transverse part, it turns out it just follows, the answer is it just follows this equation. So this e to the minus j omega naught t is the precession we talked about before. Okay? And now this is the decay. And so what you have is you start off here and you just follow this curve, and it's like a death spiral. Okay? So that's what the magnetization does. Let me switch to the PowerPoint here because there's a nice movie of that. So if we play this movie. Okay, so what that movie should look like is you'll watch this magnetization. Oops. This magnetization decays down. At the same time, this decays away, and it'll decay. And since T2 is shorter, this is still going to be recovering after that. Okay, so I'll post that movie online, and you guys can watch it. All right. And so you can also get it from this website. It's from Brian Hargraves at Stanford, and he's got a lot of nice movies. This is another way of looking at it. So essentially, here we start off with the magnetization here, and now we're looking at the mx component, the my, and the mz. Okay, and so essentially it spirals in, and then generally spirals down, and then also recovers. Okay, so both things are happening at the same time, but T2 is generally a lot shorter than T1. So generally this decays away, and then it just goes like that. All right, so that's the picture we're looking at. Okay, one last thing we have to talk about in terms of real world is what are called static inhomogeneities. And so these are things that, there's two things. One is that when we have these magnets, we try to make them really perfect. There's a lot of time spent on this process called shimming, which is trying to get the field as uniform as possible. Okay? But even if you do that, once you put in a biological sample, that sample itself will distort the field again and make it inhomogeneous. And so we need to consider what happens. And so there's really no way, it's a problem that we still face a lot. And so this idea that the field that we deal with is not homogeneous is something we need to look at. So the idea is that there's different types of, each type of material will tend to be either para or ferromagnetic, which means it will tend to concentrate the magnetic fields in it, or it'll be diamagnetic, which means it will tend to repulse the magnetic fields. Okay, so the idea is, let's say you had a very uniform field. So this is sort of representing the field lines, of a uniform field. So you spend all this, you spend $1 million to get a very uniform field. Okay, and then you put in an object into that field. And let's say that object is paramagnetic, okay? Then this object is going to tend to distort the field lines, okay? So you're no longer going to have a uniform field, all right? So one place that we encounter every day where this happens, especially in the work that I do with fMRI, is that anytime you put a person's head in the magnet, there's a lot of field inhomogeneities. In particular, these are axial views. This is what the head looks like. Okay, so what do you think? And this is the sort of the anatomy, and this is the field. Okay, so this is the sort of the darker showing a difference in field. So typically the field is fairly homogeneous here, but you notice these big divots at the front of the head. So what do you think those are due to? Why would there be such a big field inhomogeneity at the front of everyone's head? Go ahead. Calcification of pineal gland? Pineal gland, okay, which is really small though, right? Okay, so yeah, so hopefully it's fairly small in your head, otherwise you're gonna have problems. So that's due, one process. What's another factor? What do you have at the front of your head? You've got brain, right? You've got skull. You've got eyes. You've got teeth, right? You might have dental work, right? Which would certainly cause things. Does anyone know what your sinuses are? What is a sinus? Yeah, pockets of air. So it turns out you have these big pockets of air here, here, here. Anyone who has a sinus infection will know a lot about sinuses. And so those pockets of air, the susceptibility of air is very different from the susceptibility of the brain tissue. And so that change in susceptibility causes the fields to be very distorted. Okay? And so this is a problem that we face every day because it really screws up our measurements. Right? And why does that happen? Well, imagine you had something that was, in this case, this is a small dipole, okay? And it is creating a local disturbance in the magnetic field around it, all right? And so if you had spins at different locations around that dipole, they might start off in phase, but over time, because they're experiencing different fields, they're going to get out of phase. Some are going to go slower, some are going to go faster. And so over time, you're going to end up with some dephasing, okay? And so the signal is going to get less. Now let's say you increase the strength of this field here so it's even more magnetic. Now you see the fields are even more distorted. So now the spins are going to get even more out of phase, okay? And so, for example, this curve here would be decaying even faster, all right? So there's this dephasing that happens that is typically a problem because it can cause what's called signal dropouts. Now when we talk about fMRI, we're actually going to use this to our advantage, but for now it's a problem. Okay? So it turns out that these static homogeneities can be modeled by just adding this term, which is saying this sort of additional spin term that causes things to go either slower or faster. But because that's sort of complicated, we generally just approximate it as this additional T2 prime decay. We say there's an additional decay term that's going to happen. All right? And so we call that additional term T2 prime, and then the sum of those two processes. So we've got T2 decay, and we've got T2 prime decay. That combination gives us what's called T2 star. Okay, so that's shown here. All right, so that's sort of things decay anyways. They're going to decay a little faster because of static homogeneities. That overall decay is T2 star. So let's look at this. The T2 decay is due to random motion of spins. It's random, so there's no way to reverse it. Okay. It turns out the good thing, though, is that these T2 prime is due to what's called static homogeneities, things that are just there and to first order are not changing. So it turns out that those are actually reversible. And that turns out to be good because for a lot of clinical imaging, we're going to depend on this to get good images. So how do we do that? Well, what we have here is sort of our spin warp pulse sequence. We haven't really talked about this part yet. This is the RF slice selection. But we have talked about this part, which is the spin warp pulse sequence. And it turns out that if the magnetization we would have received at the echo time is here. So echo time is defined at the place where kx equals 0, ky equals 0. Let's say our object was a rect function. So let's say object equals a rect function. Then we would, if we're going through the ky equals 0, we would expect to see a sinc function, okay, the Fourier transform of our object. But because of this T2 star weighting, so we would expect to see a sinc function. But because of the T2 star weighting, we're going to see a sinc function times this e to the minus t over T2 star, okay, which is what is shown here in red. So instead of the function we expect to see, we see one that's weighted by this exponential, where this is showing the weighting term here. All right, so there's this exponential weighting. So we've gone from this amplitude down to this amplitude here. So we've lost a lot of signal due to that decay. All right, and if we wait too long, that signal is going to decay completely, and we'll have a black image. All right. So this is some examples of that. So this is somebody's head. They're actually, I believe they're probably normal, but you can sort of see that there's something going on here. So what do you think is going on with that person? They actually do have a mouth, they have teeth, they do have a jaw, but the image shows that it's all black. So why would that happen? Any idea? What? Yes? It could be, but let's assume for this case they're not talking. So they're holding as still as possible. What do people have in their mouth that might cause problems? Let's say it's a teenager. Braces, right? This person probably has braces or some other type of dental implant that is causing susceptibility in problems. Okay. Similarly, this person probably has some metal implants that are causing the magnetic field to be distorted. All right. So in general, for example, like when we do our studies, we always screen out people who have a lot of dental work because we know we're going to lose a lot of our signal. Okay. So the solution is, for certain types of imaging, you can use what's called a spin echo, which I believe was discovered by Erwin Hahn when he was a grad student at Berkeley many, many years ago. And the idea is fairly simple. Let's assume at time 0 the spins are all aligned. Okay? And then they get out of phase, such that A is a little slower and B is fastest. Okay? So you've got, imagine some spins are fast, some are slow. They're going to dephase. You can apply what's called a 180-degree pulse, which actually just flips the spins such that E now goes to the back of the line and A goes to the front of the line. Okay, so it's like you had a bunch of runners. Halfway through the course, the person at the front goes to the back, the person at the back goes to the front. And then you allow them to evolve. So the slow person at the front is going to drift back. The fast person is going to come towards the middle. And if you acquire at the right time, you've reversed that dephasing. So it's a really cute trick that is actually the key to a lot of clinical imaging. Right? I'm not going to play this movie because it's just going to crash. So, but what that movie will show, and I'll post it, is that essentially it's going to show the spins phasing, flipping, and then converging again. So the movie of what we just talked about. So how do you do that? So the pulse sequence now is, we split up the spin warp into sort of the encoding, the initial encoding, and then the readout is here. And what we do is, after the excitation pulse, we wait some amount of time, and we apply this 180-degree pulse. And if we wait the same amount of time, so in this case, the spins are dephasing, right? And then we wait the same amount of time, and then they can rephase. Then when we acquire here, most of the spins have rephased. Okay? And so now we have really recovered a lot of our signal amplitude. So this was if we, let's see, E minus T over T2. Okay, let me erase that. So at this point in time here, let's see, we have pure T2 decay. Okay, whereas before when we had the T2 star decay, I didn't draw it here, but probably we would have been down here. Okay, so if we had more decay. So we've reversed at least some of the decay, and so we actually recover some of the signal. Okay. In the worst case, when, for example, we were at the front of the mouth in that person, we'd actually have, at this point in time, if we acquired, we'd probably have no signal. Okay, all the signal would have died out in the presence of loss susceptibility. So this allows us to recover the signal. There's still some decay due to the T2, but at least to recover some signal. So this is an example of that. So this is if we don't have that refocusing pulse, we end up with all these dropouts here. Okay? And so this is places where there's a lot of changes in the field. Once we apply the spin echo image here, you see it's almost like magic. Okay, it recovers the signal. Okay, so that's pretty cool that you can actually do that. So a lot of standard sequences are T2 use the spin echo for that very reason. Okay. This is just summarizing. This is from the book. So we have the longitudinal recovery, and we also have so that's just recovery to m sub 0. And then we have T2 decay, which is due to random motion. And then the T2 star, which is random plus static. Okay? And this decay, the T2 star, is always going to be less than the T2. All right? Because it's got both the random plus an additional component. Okay, any questions about that? Okay. So we're going to spend the last 10 minutes talking about image contrast, which is basically how do we take advantage of the fact that different tissues have T1, T2, and T2 star. Okay. In addition, different tissues are going to have different densities of protons. Okay, so proton density is something else we're going to talk about. So basically, for example, cerebral spinal fluid has a very high proton density. It's basically water. Something like fat will tend to have much less proton density. Okay. So we're going to create the contrast for now by adjusting two parameters, TE, which stands for echo time, and TR, which stands for repetition time. All right. In the future lectures, we're going to talk about lots of other types of contrast, but for now, we're just going to focus on these two parameters here. Okay. So we're going to stick initially to what's called a saturation recovery sequence. Okay. Saturation means that we start at 0 transverse magnetization. So we apply a 90-degree flip angle, which tips the spins from here all the way to here. So at the beginning, m sub z is equal to 0. Okay, so at this point, after we tip the spins, m sub z is equal to 0. So anytime we start off with m sub z equals 0, it's called saturation recovery. Okay, starting up at 0, and then it's going to recover like that. All right. So in this case, this is the equation of motion for a gradient echo. We have the proton density. So this is the image intensity at every xy point. We have its proton density at that point in space. We have this longitudinal recovery, which depends on T1, okay, and that's just this curve here. And then we have this decay, T2 star decay, that looks like that. Okay, and so you can sort of see it depends on T1 and T2 star, and also the echo time is here. That's the point where I acquire my image. That's where kx is equal to 0, the center of k-space. Okay? Because remember, we said the center of k-space is where you sort of have the average of your object. And so that's the average brightness of your object is what you see at the center of k-space. So that's most objects have their peak at the center of k-space, so that tells you sort of how much signal you're going to have. Right? So this is what we talked about was a gradient echo. The spin echo is exactly the same, except we add this 180-degree pulse in. So now that T2 star becomes a T2 decay. But that's the only difference between the two for now. All right. So let's go through and talk about the different sequences. So T1 weighted sequence. So in this case, we want to get rid of this e to the minus TE over T2 star term, right? We'd like something that, so this only depends on T1, this depends on T2, right? So how do we make this term go away? What should we do with the echo time? In the ideal world, what should the echo time be to make that term have no dependence on T2 star? Louder? Go ahead. I think you had it right. Go ahead. Yeah, 0. Very good. So if TE is 0, then this just is 1, right? So the idea is we want to make TE as short as possible. In the ideal world, it'd be 0, but in general, it's going to be like a few milliseconds. All right? So for T1 weighted sequence, we want to make echo time as short as possible. So this is the sort of the principle behind T1 weighted contrast from the book. If I have a short T1, it recovers very quickly. Okay. If I have a longer T1, it recovers more slowly. Okay. So if we were to plot these on the same graph, one would recover very quickly, and the other one would recover more slowly. Okay. And so that difference in the signals we can use to create contrast. Okay. So this is exactly shown here. So I have one that's got a T1 of 800 milliseconds, the other one a T1 of 1200 milliseconds, and these are the recovery curves. Okay. And this here is the difference, the delta in the recovery curves. And so you can sort of see the difference here is maximized around, let's say, about 1,000. Okay. And so as a rule of thumb, if I have two tissues, I want to pick a T1 around the average, in which case the average is about 1,000. Okay? All right, so that's a good rule of thumb. If you've got two different tissues with different T1s, if you pick your TR, the repetition time, to be about sort of in between the two, then you're going to maximize the signal difference. All This is an example of some T1 weighted images. And so here, what we're seeing is the bright spots here are basically fat-containing lesions. Okay, and so, for example, in this image here, where is the fat located? Where in the brain do you see a lot of fat that probably shouldn't be there? Yes.
The lateral ventricles.
Right. So this area right here, right? Okay. So that generally doesn't appear like that in a normal human being if you're not having a lesion. And so in this case, this person has a fat-containing lesion. And so on a T1 weighted image, the fat recovers very quickly because it has a very short T1, so it'll appear much brighter. Okay. In T2 weighted, we want to get rid of the T1 term, which is 1 minus exp minus TR over T1. Okay. So what should I do to TR to get rid of this term here? How do I make this term go away? Yeah, if I make TR really, really long, right, this term is going to go to 0. So I'm going to make TR go to infinity. Okay. In general, but infinity is a long time, so in general it's sufficient to make it like 3 T1 or a couple T1s, and then it'll mostly decay away. So in general, for T2 weighted, I want to make the TR very long, and so I'm left with proton density and the T2 weighting. Okay. So this is an example here where we have two T2s, one at 80 and one at 120. So you see the 121 decays more slowly than the one at 80, and the difference is here. And here you see it's sort of, the peak difference is around 100. And so that's also, once again, the average. Okay, so as a rule of thumb, if you have two tissues with different T2, if you pick an echo time that's sort of midway between, that will create good contrast for you. So this is someone with a normal T2 weighted image of a brain, a normal brain, T2 weighted. This person has a big cyst here. Okay. So is the T2 in this area short or long? So this obviously has a problem. This person has a problem with their brain, right? So we're not trying to figure out what's wrong with their brain, but we're just asking from a physics point of view, in this part of the brain where it's very bright, and this is a T2 weighted image, is it a long, in that region, is the T2 longer or shorter than in, say, a normal part of the brain? Go ahead. Oh, okay, you were just stretching. Okay, sorry. Okay, so so one possibility it's longer, right? Okay. Great. So why would you say it's longer? Do you want to call a friend? Okay. Anybody want to help him out? No. Okay, yes, back there. Yeah. Right, which is a very long T2. Right. Okay. So that's one way to look at it. You could also remember that if you have two different things that are decaying at different rates, and we acquired some time here, then this signal is much brighter than this signal, right? So the red signal is going to be much more brighter, has much more signal than the blue. And clearly, this has a long T2, right? So it's decaying very slowly. So by the time you acquire it, the other tissues have decayed quite a lot, but the water that's filling that cyst, or the cerebrospinal fluid that's filling that cyst, has a very long T2, so it persists. It has hardly decayed at all. Okay. Proton density is, in this case, we want to make both the TR very long and the TE very short. So TR going to infinity, TE going to 0, and in which case we're just left with the proton density, okay, which is basically just how much water there is in that tissue. Here's an example where they're detecting a white matter change here in this area. in someone with, I forget the exact details, but I think some sort of multiple sclerosis, and the density of water is a little higher than it is in the surrounding. So this is sort of normal white matter here. And so they're arguing that there's some diffuse changes in the proton density that's indicating there's some multiple sclerosis in this subject. Okay, so what we're going to do is we're going to end here, and this is the assignment we'll pick up on Monday. So we'll start off on Monday with a few minutes for you to enter in your answers for this. But here's the question. You are given these three different tissues and the parameters, the proton density, the T1, and the T2. Okay? And you want to create a T1 weighted image, a density weighted image, and a T2 weighted image. All right? So given these parameters and the fact for each type of image, what would be a good guess for the TR and the TE that you should use to achieve either T1 weighted, density weighted, or T2 weighted image? All right, so is it clear what we're asking for? Okay, so go ahead, we'll go over the answers on Monday, but basically you can enter it. I'll open up the poll Monday morning and you can enter your answers in. Okay, any questions before we end? Okay, well have a great Thanksgiving holiday and we'll see you next week.